Yeah, hello. So I hope you had a good lunch. I will try to wake you up with a bit of cryptography. Not sure it will work, but anyway. So yeah, we want to speak about GPG memory forensic. But first of all, I'm Sylvain Pelissier. I'm a security researcher at Kudelski Security. So I mainly work on applied cryptography topics. I used to do hardware attacks in the past, and I'm occasionally a CTF player and sometimes organizer. So that's it for me. I did this work with Nils, my colleague, and I will let him introduce himself.
Thank you, Sylvain. So hello everyone, my name is Nils Amiet. I'm also a security researcher at Kudelski Security, and I'm focused on privacy and data processing at scale. And I'm also a huge Linux fan. So we'll be talking about GnuPG or GPG for those who know it. It's basically an implementation of the OpenPGP standard, and it's basically a software that lets you encrypt or sign data or messages. And example use cases of how we can use it is, for example, signing and encrypting emails. That's probably the most common use case. It's also used, for example, for signing Git commits. Many Linux distributions use it to sign their packages. And another way you could also use it, and that's pretty common, is if you want to do SSH authentication, that's also possible with GPG keys. And more recently, we've seen this was announced on the GnuPG official blog, is that the German government actually approved GnuPG VS Desktop, which is a desktop app for encrypting emails and files, for data that is classified at the VS NFD level. So that's like restricted level. It's one of the 4 data classification levels used in Germany. So it's getting some more traction recently. So here we have an example. So this is a screenshot of the open source email client Thunderbird. So for example, if you write an email, you'll see at the bottom right, there's these 2 icons. First one is just saying that the email is going to be signed, and the second one, the small lock, just shows that the email will be encrypted. And on the other side, when you receive an email and open an email with Thunderbird, there's this small button you can click that says Open PGP at the top, and you get a pop-up that shows you whether the signature of the email was valid and verified, and also shows you that the message is encrypted. So that other use case I mentioned, so signing Git commits. So if you sign a Git commit, it's either something you put in your config file, or you just pass it the arguments to sign commits. So that is going to use your GPG key to sign your Git commits. And if your GPG key is protected with a passphrase, which you should do, it's going to prompt you to enter your passphrase. And basically, every time you do such an operation, you will have to enter your passphrase unless there is something that caches it for you, and we will see that next. So one component that comes with the GPG command line tool is actually a daemon called GPG-agent. So it's a service that runs in the background. And if it's not running yet, the command line tool is going to launch it automatically on demand. So it should always be available so that the command line tool can actually use it. And basically, this daemon offers some services, such as importing keys, exporting keys, generating keys, and so on, but also getting a key from the cache that contains keys that stays there in memory, so that you do not have to enter your passphrase every time you want to do an operation with the same key, for example. And the way this works is that the command line tool and the service actually talk using a text-based protocol, which is called the ASUN protocol. And it is through that for example, the keys are accessed from the cache.
Yep. So the first security work which was done on GPG-agent was called GPG Reaper. And researchers have found out that, in fact, when a passphrase is in cache, it will stay until an action of GPG-agent is performed. Meaning that if nothing is done, it will stay in memory basically forever until a new action is done. And since there is debug mode for GPG, it will let you see all the command in ASUN protocol in clear. So meaning that if you have access to a machine, you can have the passphrase which is in cache. Basically, you will see that you have at some point the passphrase going in clear to the communication just by using the debug level guru. So the problem of the cache was solved, but this debug level is still here because it's a feature. So if there is a passphrase in cache, you can still have access with this debug level. However, for our research, we were interested to know how the cache works for GPG, how the passphrases are stored in the memory. So there is no documentation about that, but we found a comment explaining that the encryption keys are encrypted in memory, and it's done to avoid first to grab the passphrase in clear if you have a memory dump, and also at some point if users are using a TPM or physical device, this encryption key could be stored in this device, and then it will be safe. But it's not the case so far. We figure out that the encryption of the memory is done using AES key wrap mode of operation. So it's not well known, but it's used by few solutions like Cryptomator or Apple 502. So it's quite simple. An IV is inputted, which consists of A6 8 times, concatenated with the first plaintext block. Then it's encrypted with AES. So the first part of the result is XOR with a counter, concatenated with the second plaintext block, and so on. And you have to repeat this operation 6 times to obtain the encryption, the result. To decrypt data, it's the same thing in the reverse order, and you should obtain at the end the plaintext and the IV, so A6 8 times. Meaning that you have a way to verify the integrity of the decryption. If you obtain A6, you know that you have the correct decryption. Otherwise, you can just say that it's invalid. So basically, the cache items are encrypted with this mode of operation. The key is randomly generated by GPG agent at the startup. And now the key is stored somewhere in memory in clear because there is no interaction with TPM or physical security enclave. So we looked at the memory, and at some point we were able to find the 8 bytes of the passphrase in clear, and just in front the IV value A6. So it does not match the implementation. We were wondering, okay, it's really strange. It should not happen because cache item should be encrypted. So we dig a bit deeper. We figure out that indeed there is still always 8 bytes of the passphrase in clear in the memory. It was a problem of Libgcrypt, which is a cryptography library for GPG. So we reported this bug to GnuPG. It was quickly fixed. And now if you are using the latest version of Libgcrypt, there is not this problem anymore. It's correct. And the problem was, in fact, there is a mechanism to clean the sensitive data from the memory, but one temporary variable containing the last decryption of AES was not properly cleaned, so it contains the IV and the first 8 bytes of the passphrase. So it was the problem. After that, we were interested to know, okay, can we do a bit better? Can we decrypt the full passphrase, search for the cache item and decrypt the full passphrase? So we dig into the source code of GPG, and we figure out that cache items are stored in a chain list. So we have a timestamp for the creation time, a timestamp for the access time, the last access time, and the time to leave. So the number of seconds after you need to delete this cache item, and finally a pointer to the encrypted data, so the cache item itself. So we thought, okay, we can just create a regex by searching the two timestamps, creation time and access time, and also the default time to leave, which is 10 minutes, so 258 seconds in hexadecimal. And meaning that if we use, for example, this regex, we'll find all the cache items which were created between July 27, 2021 and before February 6, 2022, with a time to leave of 10 minutes. And then if we have matches to this regex, we can still verify if the created timestamp is less or equal to the access timestamp. And if not, we know it's a false positive. We can just discard this value. So we ran the regex on a memory dump. We had some results. And in fact, indeed, it was the correct cache item which was found with the creation time, access time, time to leave, and then the encrypted data. So it worked for this part. We had a way to find the encrypted cache item. Now the difficult part is how we find the AES key in memory, because it's 16 byte random in memory. It's not really easy to find, but hopefully there is a known method to do that, to recover AES key in a memory dump. And it's based on the fact that AES before encryption use AES key schedule algorithm. It will basically take the secret encryption key, which is the first sub-key here, and it will derive 10 other sub-keys with this algorithm. So we don't need to go too much into the detail here, but just we can see that it's easy to test from the memory, so sequentially, byte per byte, if the last word processed through these three operations and XOR with the first word, if it equals this word, then there is good chance we have a key schedule. We can repeat this if it's okay. If it's not okay, we can discard. It's not a good key. And if it holds, we can test the second word, the third word, and the fourth word. And then there is a high probability that we have a AES key in memory. So that's the way we did to identify the key in memory. So this gives us a full recipe to find the cache item in memory. So regular expression, AES wrap key with the method I found, and we can check the integrity to be sure we decrypt it properly. So this is the idea, and now I will let Nils explain how we implemented it in practice.
Thank you, Sylvain. So first, before explaining how we implemented this, I have to introduce something which is called volatility. So if you don't know about it, volatility is an open source framework that you can use to extract information from a memory dump. So some use cases of that is to do memory forensics, for example, retrieving secret keys. That could also be used for getting, for example, the history of commands that someone has typed in their terminal, also for malware analysis, and basically anything that you'd want to do after the fact, where you have, for example, a running system, and you want to do like a snapshot of the memory at a specific point in time for later analysis. And this framework, Volatility, has a plugin system. So it's actually cool so that you can build your own plugins to extract data from memory. And one example of such plugins is a plugin that was developed by Martin Ulikovsky. And this is a plugin that lets you recover Bitlocker keys. So if you don't know about Bitlocker, that's basically Microsoft's official implementation of a full disk encryption. for Windows OSs, and basically when you first unlock your full disk, the key is going to stay in memory, and if you put your machine into hibernation, that is also going to be saved to a file, and you could, for example, retrieve that key either from memory or from a hibernation file. And the idea here is that this plugin uses the technique that Sylvain just showed. And when you want to use these plugins with Volatility, here you have an example, but this is basically an example using an old version of Volatility. The latest one is Volatility 3, but this plugin was made for Volatility 2. So the main difference is you have this profile argument that does not exist anymore in Volatility 3. You don't need that anymore. But the idea is you just pass it the file that contains your memory dump and the name of the plugin you want to use. So here the Bitlocker plugin. And in the output, you see that it finds the FVEK, so the full volume encryption key. So what we did in this work is we made two plugins for Volatility. So the first one is able to retrieve partial GPG key passphrases, and by partial I mean up to 8 characters, but that's using basically the bug that we reported, where it stayed in memory. And the second plugin actually does the whole thing, and it retrieves the full passphrase, and therefore you can use it to decrypt the ciphertext and retrieve the plaintext from the memory dump. And we have open sourced these plugins, and they should be available at that address right after the talk. So time for a quick demo of those plugins. So here I'm going to run the first plugin, so the partial plugin. So as you can see, I'm just running Volatility 3. I pass it this file, which is our memory dump. And I also tell it, like, where is our plugin, the name of the plugin, and some symbol tables. This is something you need when you run Volatility 3. This is explained in the documentation, basically. When you run it, you immediately see that we can find the first 8 characters of the passphrase that was used to encrypt some file when at the time we did the memory dump. And the second plugin, so this one is the GPG full plugin. So it's basically the same thing, except that it's going to find the whole passphrase that you can see here. So this is what I just showed. So use cases. So basically, how can you use these plugins? So imagine you have like someone who is a bad hacker, let's say, and the police makes a raid and gets access to their computer physically, and when they do the raid, they access, let's say, for example, such as this laptop. It's just opened, unlocked, and running, and they want to do some analysis, maybe to recover some conversations that were encrypted. But the problem is when you have such a system, you sometimes do not want to mess with the running system. So what you generally do is you make a snapshot of the whole memory at a specific point in time, and then you want to analyze it after the fact, offline, as you want, basically. So here you could use this plugin after you have made a snapshot of the full memory to retrieve the passphrase, unlock private GPG keys that were used maybe to encrypt some secret files or conversations, emails, whatever, and decrypt these conversations and retrieve the private conversations. Another use case is ransomware. So what we've seen in the past is that some ransomware are actually using GPG under the hood to encrypt files. So here we have 3 examples of those: KeyBTC, Voltcrypt, and QWERTY. These use GPG to encrypt files. And usually what they do is they only use asymmetric or public key cryptography to encrypt the files. So the problem is that these, the passphrase or whatever is not going to be stored in the cache. But we could imagine that some ransomware wants to do encryption with better performance. And since usually a ransomware encrypts a lot of files, like when you get infected, they will try to encrypt your whole files, basically. You still have to do like asymmetric operations for each file. So it would make sense for a ransomware to use a symmetric key for encryption. And if that happens, basically what it would do is it would have two keys. So it would have a session key that's going to be used to encrypt the files symmetrically directly, and another key that we would call the master key that just encrypts this session key. And only the attacker, the bad guy who infects people with their ransomware, is going to have the private master key, so only them would be able to recover the encrypted files, basically. So if that happens, and let's say we get infected with such a ransomware, we do a full system memory dump, and the master private key's passphrase stays in memory. Then, using that plugin, we could recover it, unlock the private key, use the private key to decrypt the session key, and use the session key to decrypt the files, and therefore recover all the files that were encrypted by the ransomware, and make the ransomware ineffective, basically. So here it's a very short example of how this could be implemented in a few lines of bash, basically. So what you see is on lines 3 to 5, we just have a hard-coded master public key. And then on lines 7 and 8, we just generate, line 7, we import that key. Lines 8 and 9, we generate a random session key and write it to a file called sessionkey.txt. Then on line 10, we use the master key. GPG crypter is just the key that corresponds to lines 3 to 5, to encrypt the session key file. So this gives an output which is the encrypted session key. Then we delete the original non-encrypted session key, and we use the one that stayed in the session key variable to encrypt files we want to lock, basically to infect the victim. In the end, we delete the session key from memory, and we delete the clear text files. So we are only left with encrypted or /infected files. So yeah, basically, if such a ransomware existed, we could use the plugin to recover the key and the clear text file. So let's see now conclude.
So that's it for us. So yeah, we've seen that cleaning memory from sensitive data is hard. Even for GnuPG, which already implements some form of memory protection and cleaning sensitive data, but it should be tested in practice to see if there is nothing left in memory which are sensitive. And also, if you want to use GPG and be protected against such attacks, so such dump of analysis of memory dump, then we need to use a TPM or a secure enclave to protect the encryption key. For the plugin perspective, also we'll work a bit more on the plugin. So far, we support only Linux operating system. We would like to adapt it to Windows, and we need something to adapt with Volatility. And also, we would like to have a way to automatically detect the timestamp at which time the VM, for example, started, to not guess at what time, which timestamp we need to input to the plugin. So thank you for your attention, and if you have any question, we have time to answer or during the conference as well.
Thank you. Okay, thanks for the talk. Actually, quite interesting. I have sort of dumb question. I don't know if it's a proper question, but have you tried with the same mechanism that you utilize to identify the partial keys and the full keys in memory to actually develop something to clean the memory after that? So I'm trying to understand if with the same methods we use to identify the keys cached in memory, we can do some cleanup after. Because, for example, in the ransomware case, I get it. It's nice to have the keys cached. But what happens if I'm using GPG to something security sensitive? What mechanisms do I have in place to double check and do my due diligence to clean the memory? So that's the question.
Well, basically, you can say that you don't want to use a cache. You can put a time to live of 0, I think. -1 is for infinite time, and 0 is like no cache, which won't cache the passphrase in memory. So one solution. I mean, you can run the plugin, but you have to dump the memory of your of your computer, and then run the plugin to see if there is something in the memory. So, and then there is no way to. I mean, so far it's how GnuPG works. You have the encryption of the memory, encryption key of the memory, which is unclear in memory. So there is no way to really prevent that so far. So, thank you.